Hi, everyone, and thank you for being here. I'm Razvan. I work for Adobe with a bunch of awesome people on some interesting things like CSS shapes, masking, CSS blend modes, CSS regions. Some of you may know me for building the CSS Shapes Editor Chrome extension, which allows you to edit shapes in the browser. In general, I work on practical things. None of that matters for today, because today, I want to show you something which I'm fascinated about, and that is unconventional uses of technology to transmit data and input. This isn't so much a talk, but actually just a collection of demos I built or other people have built, and stories which I found really interesting in the sense that they use technology in unexpected ways with unexpected results. So today I'm going to go briefly into sound, how we can transmit data using sound, and how we can build our own cheap version of the leap motion just using sound, your laptop. Then I'm going to talk about a way of using light to communicate to your computer, and if there's time at the end, 2 short stories about interesting ways to transmit input to devices. So without further ado, let's begin. The year's 2013, October. I come across this article on Ars Technica, and it's about a respected security researcher who supposedly found this very sophisticated piece of malware. This was infecting the BIOS of his machines, and it was spreading by ultrasound. What's more devious about it is that it couldn't be diagnosed with forensics tools, and it didn't leave any traces. Now, that was odd. This guy found out that ultrasound was the means of infection by repeatedly removing stuff from the computer. So he removed the hard drive. He removed the network interface. He removed the memory. He changed so many components. And it wasn't until he actually removed the sound card, which was controlling the speakers and the microphone, that the infection stopped. Now, these claims are being contested by other security researchers who haven't been able to reproduce the same effects using the logs. But other security researchers have proved that it is actually possible to infect the BIOS of another computer just using ultrasound. Quite scary, if you ask me. Around the same time, Boris Mus, he's an engineer for Google, he was playing around with the web audio API, and he was trying to send data between devices using messages encoded as ultrasound. And he put together this library called sonicnet.js, which I'm going to use today. And the way this works is that it takes a part of the sound spectrum, specifically the part where you can't hear the ultrasound spectrum, and it chunks that into various bits and pieces, and each letter of the alphabet gets a portion of this ultrasound spectrum. So when you want to send a message, you essentially encode this as ultrasound and send it in a frequency which, as us as adults, we can't hear. Some pets can hear it, and small children. But it's kind of invisible or inaudible. But rather than talk about it, I want to show you a demo. Full disclosure, this is a demo idea I took from Boris's original experiments. I just adapted it for this presentation. So all credit goes to him on that. What I'm going to do over here, exit full screen mode, and on the right-hand side of the screen, you're going to see that I have this demo running on 2 devices. One of them is my laptop, and the other one is a phone, which I have connected over here via cable. They're both running the same demo, and what I'm going to try and do is try to get them synchronized just using ultrasound. And I really, really hope this works, because there's so many things to go wrong with the demos today. OK, so just to get a sense of what's going on over here, I'm going to turn on the visualizer. So this is bouncing around because it's hearing me speak. But as I'm going to click on the icons on each one of the devices, they are going to send out a message in encoded ultrasound, and you're going to see a distinct peak towards the right-hand side of the spectrum over there. So let's try this. I'm going to start with my phone and start sending emoticons to my laptop. It works. It works. Ah! OK. Thank you. OK, this is unexpected. It works. Most of the time, it works. So you see my laptop's picking up the ultrasound from the phone, which it's emitting down. The phone itself, sometimes it doesn't actually catch its own ultrasound back. So the speakers is over here, and the microphone is down here. And there is actually a big caveat with microphones on phones. They're optimized for speech, not necessarily for ultrasound. This is one of the few devices I have which actually works with this. But if you don't have ultrasound-capable devices, you can do the other thing in reverse. You can use audible sound spectrum. So I'm going to switch both devices to audible. OK, allow. And this is going to blast out a very annoying high-pitched sound, but it's essentially doing the same thing. So I'm going to try this with my laptop now. You can probably pick it up through my microphone. OK, good. It worked. You can't believe how happy I am this works. I've tried it so many times. But all props to Boris, who built the SonicNet library. His work is amazing, and essentially, he should be getting the applause. Right, so use cases for this. We synchronize two devices. Google used this library with a few modifications to build Google Tone. This is a browser extension which allows people who have the same extension to share links between them just using audible sound. It has a nicer sound, but essentially, if you're in the room with someone and you want to share a link, you just press a button, and your laptop just speaks the link towards the other device, which is kind of cool. It works over Hangouts. It works over a lot of things. Nobody has to install everything more than Chrome in this extension. The big problem with this, though, is that you have to your laptop is always listening to the environment so it can pick up these links. And I don't know about you, but that kind of creeps me out, so I don't use it. Nonetheless, very cool extension. OK, switching gears now to motion sensing using ultrasound. This one's very cool. So the Doppler effect. You've all experienced this. The Doppler effect is this phenomenon of the apparent frequency shift of a wave to a static observer as the wave is being emitted by something in motion. So imagine the last time you heard an ambulance siren. As the ambulance is traveling towards you, you're hearing a higher and higher pitch. And the reason for that is that the source of the sound, the ambulance, is traveling, and each sound wave has to travel less and less to get to your ear. Therefore, you're going to have more sound waves hitting your ear as the ambulance travels towards you. The same thing happens in reverse. As the ambulance goes away from you, sound waves have to travel longer and longer to get to you because the source of the sound is going away from you. Therefore, the pitch sounds like it's going lower and lower. And this is one of the fundamental principles in radar. In radar, you have a base station which is emitting a radio frequency, and it's listening for that same frequency around the same spectrum. Those radio frequencies are going to bounce back everything they hit. So if you have an airplane in motion coming towards you, the radar is able to use the Doppler effect and a lot more technology and maths than I'm capable of to basically determine if the airplane is coming towards it or going away. And then using an array of radar systems, you actually know where that airplane is in space by triangulating the sound. OK, we have everything we need to build a radar system in our computers. So first of all, we can replace the base station with our laptop speakers, and we have the microphone over there. And then we can use our hand to basically understand where it is in relationship to the speakers. And how we're going to do that? We're going to use ultrasound. Daniel Rapp built this very cool small library called Doppler. What Doppler does is it sends out an ultrasound from my laptop speakers, and it's also listening back for the same frequency. What you're seeing on screen right now, once it settles, is actually my laptop emitting around 20 kilohertz sound. You can't hear it, I can hear it, but it's here. This graph on screen here is showing you the difference between the frequency emitted and what's coming back. So as I introduce something close in the vicinity of the speakers, like my hand and I'm wiggling around, I'm able to affect the way the echo is going back. Remember the radar and the Doppler effect. So I can pull up, and essentially, that's changing the way the sound is reflecting back into the speakers. Or I can push down. I know, it's awesome. Thank you. Right, so what can we do with this? We're getting quite a lot of resolution here with my hand, but we can only look at the peaks, and we can tie these to something. Like, for example, let's say we want to scale a balloon. So I can just do these ample gestures, or hit it so it goes right back down. There you go. Very cool. This is like the poor man's version of the leap motion. Therefore, we can use it for something practical. There you go. We have some interference. But I can use like these gestures to scroll a page up and down, so I don't actually have to use my mouse. This is absolutely interesting. So you clapping are affecting my demo, but please do that. It's fine. Because this is actually changing the echo in the room. My laptop picks up a different sort of echo as people are moving across the room, which is kind of cool. All right, so, well, if we can do these things, we can turn it into Darth Vader and just turn on Doppler navigation for the entire presentation. So I can say, I want to go back. You've seen this before, or I'm going to want to go forward. Do we want to plug in for reveal with this? Yeah, we do. OK, that was sound, and I'm glad those demos worked. Let's move over to light. So I want to talk about light. The man on the left-hand side of the screen over there is using a device called a heliograph. Now, a heliograph is a very simple system of mirrors which focuses sunlight towards a target which is farther away. And using a simple system of levers, the operator can basically flash light towards the target on and off. You can encode, essentially, Morse code, sending it to the other person listening to you. At the other end, there's somebody else, either with a sighting scope or with another heliograph aligned. And what's cool about this is that you can get about 10 miles of range for every inch of the mirror, which is kind of amazing. The record for range held by a heliograph team is 300 kilometers. Yes, between two mountains using mirrors about 8 inches in diameter. And this was happening in 1895. That's cool. There's only one drawback to this amazing device. If there's no sun, there's no messages. There's your limitation. If it's rainy, we stop. So the design evolved. It evolved to this device, which is called a signaling lamp, and it's still being used by navies today in exercises where they have to maintain radio silence. So instead of the sun, you have a very bright light inside of the device over there and a series of shutters in front of it. The operator is using that lever on the side to open and close the shutters, therefore encoding a message in, say, Morse code to a receiver at the other end. Bear this in mind as I continue. Ambient light events. The ambient light events API is something your computer has to essentially detect the light level in the room and adapt your screen intensity to the light intensity in the room. So right now we have about 42 lux. There's nothing changing over there. If I put my hand in front of the light sensor over here, you see that's going down. Or I can do something else. I can turn on a flashlight, and you see that's going to go really, really high. There you go. It's off the charts. It's absolutely off the charts. OK. This, like the textbook example for ambient light events is to adapt the page so you get better readability in low light conditions. So if I put my hand in front of the light sensor, which is next to my camera, that's going to reduce the light. I can change the document style sheet so it's better to read in low light. As I put my hand away, I can read it, therefore the style sheet changes. And I can do this over and over again. But notice that my hand doesn't really affect too much of the light sensor. The values is pretty low. Remember the signaling lamp, right? What if we use ambient light events and Morse code? What if we can send messages in Morse code to the computer just using that light sensor? Let's try my most brittle demo ever. OK. This is optical Morse code. So I'm going to turn on an application on my phone which sends SOS. It sends any message in Morse code as flashes of light. So I'm going to try and send an SOS to my computer. OK. So SOS is essentially 3 dots, 3 dashes, 3 dots. That's a S. It's really going off the chart over there, which is good. I like that. you go. It worked. Cool. Thank you. Thank you so much. So just in case you're thinking, oh, this is a very engineered demo, it only works for SOS, I'm going to try and type something longer like JSConf. JSConf. And this is going to take a while, actually. So let's try JSConf. One thing to note about the ambient light sensor is that this is not a stream. You're going to get events from the light sensor going up and down, but you're not going to get them in a very predictable fashion. So I had to build a very simple sampler. It's basically sampling the light sensor once every frame, so it's really hitting it hard, so I can decode those messages. Come on, F is always difficult. JSConf. Yes! It worked. So happy about it. I'm particularly happy that this thing worked because it shouldn't. The reason is, so you could argue, this thing only works in Firefox, and it's only in Chrome behind the flag, so you need to enable it. You could argue, well, you should turn on the camera, and you can listen to the ambient light event with a much higher frequency. Sorry, you can listen to the camera and decode the images in the camera. But there's only one small problem. You need to ask the user for permission to use their camera. You don't need to ask them for permission to use the ambient light sensor. And this is a major privacy concern. And the people writing the spec thought about this. That's why you're not going to get very predictable and accurate results from the light sensor. Essentially, because you can do a lo-fi alternative to Bluetooth beacons. You can fingerprint people without their knowledge. So here's a use case. You're walking around the store, a phone in hand, using an application, and that application is monitoring light change events. You want to enter a store, a light above your head at the entrance is flashing a very distinct pattern. Your application knows you went into the store. You go to an aisle. A different light is flashing a different sort of pattern. The application knows you're in that aisle. Therefore, it can push a notification, it can do analytics, it can do anything. You go to the checkout. You have a different light pulsating in a different pattern. The application knows you have paid. You understand what's going on over here. It sounds a bit dystopian. And if it sounds too improbable, it shouldn't, because this thing happened. This is an experiment that Philips did with a major retailer in France. And they're using a technology called VLC, Visible Light Communication. And the way this works is that it attaches a microcontroller to normal LED light bulbs, and it causes them to flash in a very distinct pattern, which we as humans can't observe, but sensors on our phones can. So what essentially they built, they meshed out the entire store with different lights, so you can build an indoor GPS navigation system for that store. You can ask for directions to go to the toilet paper aisle, and it will give those directions to you, which is kind of cool. But obviously, you need to offer permissions to do this. So this wasn't necessarily a privacy infringement, but a very, very cool experiment. The technology is called VLC, Visible Light Communication, and I strongly urge you to go look into it. Some people see this as the future beyond Wi-Fi, mainly because it has 10,000 times more spectrum than radio Wi-Fi, which is kind of cool. But this isn't anything new. This is the Timex Data Link watch. You could call this being like the grandfather of smartwatches nowadays. This was first marketed in 1994, and the special thing about it is that you could store phone numbers or to-do lists on your watch. But that's not very interesting. The interesting bit is how you got those things to your watch. And it doesn't use a cable, it uses light. So above the display over there at the 12th hour, there's a small camera. And that camera, coupled with an application for your computer, is going to receive light pulses from your monitor and encode them as messages. But rather than explain how this works, I would want to show you the commercial for the Timex Data Link watch from 1994. And this is where I'm going to need the help from the sound people, because I connected my sound, and this is something you need to hear. We're all good? We're good.
The revolutionary new Timex Data Link watch uses light beams to transfer dates and data from your computer to your wrist with just a touch of your paw. Pretty smart, eh? The Timex Data Link watch.
The cat always wins. Yeah, I find it funny. The cat always wins. Dogs have no chance. The dog's going to get it. OK, so this was 1994. That was 21 years ago. Some of the people in this room today weren't even born when people were trying out technology like this. So let's fast forward 21 years. Where are we today? This thing is called the Michigan Micromote. By all accounts, this is the smallest computer in the world right now. That's not a huge coin. That's an actual coin, and the computer fits on the side of the coin. It has everything you need. It has a processor. It has memory. It has storage. It has a small battery. It has radio. It has some sensors, like temperature and light sensors. And it all fits on the side of a coin. So this size begs the question, how do you actually, there's no room to put a connector. How do you program this thing? How do you charge it? And the answer is, you use light. The Micromote is initially programmed with light pulses. And by the way, the Micromote is the tiny black thing underneath the light bulb over there. That's the entire computer. So its initial programming phase is done by light pulses up until it boots up and turns on the radio, so it then can use the network to get further instructions. This is absolutely incredible. I am both amazed and terrified at the size of computers. OK. Since I have a bit more time left, I'm going to go into the other section, and this is my favorite one. This device is called the Misfit Shine. It's one of the early fitness trackers, and in their Kickstarter video, they alleged that their device would synchronize by you placing it on the screen of your phone. And people went crazy for it, myself included. We didn't know how this was going to be done. We were very curious, myself included. Is it rhythmically tapping on the screen to get those messages, like something like Morse code tapping? Is it generating its own electrical field, like electromagnetic field? Sadly, no. The Misfit Shine eventually launched, and the answer is it's just using Bluetooth Low Energy, which is useful because it's a high bandwidth way of transmitting data. You're a lot less prone to errors. But, and the important bit is that it uses Bluetooth in a very, very low frequency, so you need to keep it very close to your device. So that's why they invented this idea of you need to put it on the screen for it to synchronize. But actually, it would synchronize if you put it next to the phone and just tap that circle over there. A bit disappointed. But it's not totally impossible to do that. This is the Google Cardboard. Most people in the room probably know what this is. This is one of the low-cost VR headset. It's basically a piece of cardboard. You open an application, you put your phone in there, you put it up to your head, and you're projecting into a 3D virtual world. But that introduces a problem. And the problem is, how do you actually interact with your phone when it's in a box stuck to your head? And you could try using the camera, or you could try using the microphone, but those need user permissions, first of all, an extra step. They're going to drain the battery very fast. And if you're in a noisy environment or in an environment with a lot of light, they may not be that precise to begin with. So the engineers come up with a brilliant solution. On the side there, you're going to see a circular metal disc. That's a magnet. And it travels up and down in a groove. On the other side, there's another magnet which stays fixed. And as you pull the magnets, you're actually changing the electromagnetic field between those. So the engineers for the Google Cardboard app are looking with the magnetometer for the changes in the electromagnetic field. This is the same sensor you're using for the compass. And therefore, that's your input device. You can register clicks, you can register long presses just by measuring the changes detected by the magnetometer. Absolutely brilliant. Unfortunately, we can't do this in browsers today. I would love to show you a demo like this. But the truth is, we don't have access to most of the APIs in our phones. We have capable browsers, but they don't know much about the underlying sensors. And if there's any practical takeaway from this presentation today is that if you want access to all of the sensors to your devices in your browser to build your own unconventional uses of them, I encourage you to get involved in the generic web sensor API. It's at this URL. It's an ongoing specification to make a uniform way of exposing sensors for us in browsers to use. Because until we have access to the sensors on the device, native is fundamentally going to be ahead of the web. So we need access to sensors. And that's about it for my presentation. I hope you enjoyed it. I hope you found some bits of insight. And I encourage you to look for your own unconventional ways of transmitting data and input in whatever you do with your devices. Thank you for your attention.